You already know that the first 26 propositions in Book 1 of Euclid's Elements are valid not only in Euclidean geometry, but also in hyperbolic geometry and with minor exceptions in spherical geometry. Now we're going to explore some propositions from Book 3, which turn out to be valid not only in Euclidean geometry, but in Minkowskian geometry. So whereas previously we were comparing Euclidean geometry with hyperbolic geometries that use different styles of length measure, now what we're going to do is compare Euclidean geometry with Minkowskian geometry, which uses the same parabolic style of length measure, so that parallels are unique, but which uses hyperbolic angle measure. And it will turn out that several of the propositions about circles are valid in Minkowskian geometry, and furthermore, Euclid's proofs work exactly the same way as in Euclidean geometry. Let's start with a quick review of Timelike and Spacelike. In Minkowskian geometry, the points represent events. An event has a time coordinate and a space coordinate. You can think of an event as something that happens, for example, on board a moving train, and you will see that if you use the train track as your frame of reference, the time and space coordinates that you assign to that event will be different than if you use a frame of reference that's moving along with the train. If someone sits down in the dining car, that person will eat the main course and the dessert at different times in the same location, whereas someone peering in through the windows of the moving train will see those events happen at quite different locations along the track. If I consider a pair of events, then I get a vector with two components which measures the separation between the two events. The first component is the separation in time. The second is the separation in space. And in Minkowskian geometry, we've changed the sign in the dot product, so the squared length of this vector is delta t squared minus delta x squared. For convenience, if we measure time in years, we will measure distances in light years. If we measure time in nanoseconds, we will measure distance in feet. With either choice, the speed of light has the numerical value of 1. Now there are two cases. If this squared length is positive, then the space separation is less than the time separation, and we call the overall separation between the two events timelike. What this means is that you can find a frame of reference where the events are separated only in time. They happen at the same position, but at different times. If, on the other hand, the squared length of this vector is negative, then we call the separation between the two events spacelike. This is a little harder to visualize, but in this case, what you can do is to find a frame of reference where the two events take place at the same time, but in different locations. And if you take this negative squared length, drop the minus sign, and take the square root, you get the separation in space between the two events in the frame of reference where they're simultaneous. If you want to go deeply into the issue of simultaneity, I'm afraid you're going to have to take a physics course and study the theory of relativity in more detail. Given two events in Minkowskian geometry, they may be joined by a line, but that only happens if the slope of the line is less than 1 in magnitude. In that case, the line describes a uniform motion taking place at a speed less than the speed of light, which is on hand for both event A and event B. If I have events C and D with a spacelike separation, I can draw a dotted line between them. Such a line is not strictly speaking a line of Minkowskian geometry, but it will turn out to be quite useful for constructions. Now let's define angles. The square of a timelike vector is greater than 1, or is positive, and if I define two unit vectors, then I can define the angle between them as being the hyperbolic cosine of the Minkowski dot product of the two unit vectors. This dot product is always greater than 1, so its hyperbolic cosine is always well defined. If there's an angle alpha in Minkowskian geometry between some line and a horizontal line, then we'll call the slope of that line, in the Euclidean sense, m, and the significance of m is that it describes the velocity of a uniform motion that makes an angle alpha with the horizontal line, which represents something at rest. If I have two spacelike unit vectors, their dot product is guaranteed to be negative, and in fact, it's smaller than -1. So if I change the sign, I can again take the inverse hyperbolic cosine to get a hyperbolic angle. So while spacelike lines are not valid in Minkowskian geometry, we will sometimes have occasion to talk about the angle between two spacelike vectors. However, we can't define an angle between a timelike vector and a spacelike vector, except in one special case. The special case is where the dot product is 0. In that case, it's reasonable to call the lines orthogonal, and on a diagram for Minkowskian geometry, the slope of one of those lines is then the reciprocal of the slope of the other. So we have a simple criterion for recognizing orthogonal lines. Now let's talk about circles. Here's the center of the circle at O. Here is an event B in the future of O. And if we want to make a circle that has B on its circumference, all we do is have spaceships head out from O at various speeds, and we instruct the captains of the spaceships to travel until the reading on the ship's clock has the same value as for OB, and drop out a space buoy or something like that. Those space buoys all have the same timelike separation from the center O. They form a circle. If we plot them in a plane, we get a hyperbola. We can also do the same thing with events like A that are in the past of O. Once we've done that, the line AB, which has O as its midpoint, is a diameter of the circle. Now, how do we find the center of the circle? Well, Euclid tells us how to do it in Book 3, Proposition 1. What Euclid says is find 2 points on the circle. Here, 2 events A and B. Join those 2 points on the circle by a line. It's a space-like line here, and construct its midpoint. Once you've found the midpoint of a chord of a circle, all you have to do is construct the line perpendicular to it, and you will have a diameter of the circle. In this case, this line has a slope that looks like about -4 to me. So I construct an orthogonal line whose slope is -1/4, and when I draw that line, it will pass through the center of the circle. It will hit the other branch of the hyperbola. It will reach the circle again at point C, and Euclid says once we have these 2 points of intersection with the diameter of the circle, the midpoint of that segment is the center of the circle. So Euclid's construction works exactly the same way in Minkowski geometry as in Euclidean geometry. What about constructing a triangle whose side lengths have been specified? This is Book 1, Proposition 22. And the only interesting twist in Minkowskian geometry is that the triangle inequality is reversed. A straight line is the longest distance between 2 points, and therefore we have to insist that one side of the triangle has a length that exceeds the lengths of the other 2 sides combined. Then we proceed as Euclid does. We lay out on a line that I've chosen to be horizontal. Euclid does the same thing. The longest side from F to G. At F, we construct a circle whose radius is one of the other side lengths. At G, we construct a circle whose radius is the third side length. And the point K where they intersect is the desired third vertex of the triangle. Here is the longest side. Here is the second longest side. Here is the shortest side. And you'll notice that the triangle inequality holds. The sum of these 2 lengths is less than this length. What that means physically is if you travel from F to K, 1 year elapses on your ship's clock. If you then reverse direction and travel for 1.39 years, you end up at G, and you discover that for a spaceship that was on hand for both F and G, it could actually just have stayed at rest. The elapsed time is 3 years. Moving clocks run slow. So far, we've looked at circles whose radius is time-like, but we can equally well construct circles with a space-like radius. Such a circle has the property that every point on it has the same space-like separation from the center of the circle at O. An annoying feature of such a circle is that a diameter or a radius has a slope whose magnitude exceeds 1, and it's a space-like line. On the other hand, what is orthogonal to a diameter? Answer, a tangent. So in this case, tangents to the circle will be valid lines of Minkowskian geometry, and so will chords of the circle. So if we're looking to generalize Euclid's theorems about chords and tangents, these circles are just what we want. So let's look at Book 3, Proposition 16. In that proposition, Euclid says, if you construct the line orthogonal to a radius of a circle, that line touches but does not cut the circle. In other words, it's tangent to the circle. The same thing is true in Minkowskian geometry. Here is a space-like radius of this circle. Here is a line that's orthogonal to it. We know that because this slope times that slope is equal to 1. The slopes are reciprocals of one another. And sure enough, this orthogonal line is the tangent to the circle at A. One of Euclid's nicest constructions involving circles is his construction of tangent lines drawn to a circle from points outside the circle. And it turns out the same construction works in Minkowskian geometry. There's only one catch. If you want to draw a tangent to a Euclidean circle, then you need to start at a point that's more than 1 radius away from the center of the circle. Whereas if you want to do the same thing in Minkowskian geometry, you have to use a point whose distance from the center of the circle is less than 1 radius. So here's my circle. It goes through D. And what I want to do is to construct the 2 tangents to that circle from point A. What does Euclid say to do? He says, extend the line EA until it hits the circle at D. Then construct a line orthogonal to that radius. It'll be tangent to the circle, and extend it out till it cuts the circle through A at point F and point G. Having constructed the points F and G, says Euclid, now draw radii that pass from the center of the circles through F, giving point B, and through G, giving point C. And when you've done that, you will discover that AB and AC are tangent to the circle. It works exactly the same way with hyperbolas in Minkowskian geometry as it did with circles in Euclidean geometry. Another very nice theorem of Euclid's is that if you consider 2 points on the circumference of the circle and join them both to the center of the circle, the resulting angle is precisely twice as large as if you join them both to another point on the circle itself. And this is true in Minkowskian geometry also. Here I have points B and C joined to another point on the same circle. Now, if I join them both to the center of the circle, I've got a little problem. These are 2 spacelike lines. These are 2 timelike lines. These are 2 spacelike lines. And I'd really like to compare angles between timelike lines in both cases. No problem. A tangent to a circle is orthogonal to the radius, so I simply use, in place of BE, the tangent at B, which is orthogonal to it, and in place of EC, which is spacelike, I use the tangent at C, which is orthogonal to that line. And then the angle between the 2 tangents is equal to the angle between the 2 radii. And what we discover is the angle between these 2 tangents, which is equal to the angle at the center of the circle, is precisely twice as large as the angle between the 2 chords. And the proof of this is basically the same in Minkowskian geometry as in Euclidean geometry. Closely related to that theorem is the proposition that says in a segment of the circle, the angle is constant. And the same thing is true in Minkowskian geometry. If we take 2 points A and E on the circle and form angles by joining them to other points like B or C or D, it turns out all these angles have exactly the same measure. And it's even a little bit better than that. If I pick points B and D to start with, I can choose a point C in between them and construct the angle between this line and this line extended, or I can construct the angle at A between these 2 timelike lines, or I can construct the angle at E, where strictly speaking I should take the angle between this forward vector and that forward vector. But all 3 of those angles turn out to be equal to one another. Well, a special case of that result is that an angle inscribed in a semicircle is a right angle. Now this is going to pose a bit of a problem for us. How do we recognize a semicircle? We know that we've got a semicircle when it's cut off by a diameter. But a diameter of the circle has to pass through the center. It has to be spacelike. So if I start at B and form a diameter, I end up at C. So now I have a situation where both A and B are joined to C by diameters of the circle. So what have we got here? We have the 2 ends of a diameter. AC is a diameter. And we join the 2 ends of the diameter to the same point, to point B. That's exactly like forming a triangle inside a circle by joining the two ends of a diameter to another point on the circle. In this case, one of those lines is going to be timelike, the other is going to be spacelike, but that's just fine because what does Euclid say? He says under these circumstances, the angle at B is a right angle. These lines joining B to the two ends of a diameter are orthogonal, and indeed they are. One is spacelike, the other is timelike, and they have slopes that are reciprocals of one another. Book 3, Proposition 35 says that if you have two intersecting chords in a circle, then AE times EC is equal to BE times ED. Euclid's proof of this is rather tedious because he has not yet introduced the concept of similar triangles. And as a result, the only proof he can come up with is rather convoluted. So I have not tried to extend Euclid's proof of this to Minkowskian geometry. I've confined myself to verifying that the theorem is indeed valid. That is, if you use hyperbolic length AE times hyperbolic length EC, that's the same as the product of the hyperbolic lengths BE and ED. But there's another possibility here. We could have two chords of a circle that connect opposite branches of the hyperbola. And that's the situation here. AB are on one branch of the hyperbola, CD are on the other branch. They're both on the same circle. And if I join A to C and B to D, they're intersecting chords. They intersect at point E. It turns out in this case also, all these lines are timelike, and the Minkowski length of this times the Minkowski length of that equals the Minkowski length of this red segment times the Minkowski length of the other red segment. And to finish up, let's look at the alternative case where we have a chord of a circle that is extended out to a point outside the circle. In this case, what Euclid proves in proposition 36 is that the length of CD, the distance from D to the first intersection point of the chord, times AD, the distance to the second intersection point of the chord, is equal to the square of the length of the tangent line to the circle at B from D. And the same thing is true in Minkowskian geometry. If you take the the Minkowskian length CD and multiply it by the Minkowskian length dA, the result is the square of the Minkowskian length BD. So yet again, the theorem that's true in Euclidean geometry is true in Minkowskian geometry. And when I present these to you in R, you will see numerical confirmation of all these results.